Hey everyone, welcome to the very first video in our series on the reactions of chapter 9. So we just got done with chapter 8. So chapter 8 was reactions of alkenes, reactions of double bonds. This means that in chapter 9, we're going to be talking about something very similar, which is reactions of alkynes or reactions of triple bonds. So a lot of the reactions in this chapter are going to be very similar to the reactions in chapter 8. Case in point is going to be the first reaction we're going to talk about here, which is hydrohalogenation of alkynes or addition of HX to alkynes. Okay, this is going to look very, very similar to the reaction in alkenes. So like I said, this is hydrohalogenation of alkynes. So similar to how hydrohalogenation of alkenes worked, hydrohalogenation of alkynes is Markovnikov. And I'm not going to say it forms both enantiomers, but I am going to say that it forms both isomers. And we'll see kind of what that means here in just a second, okay? So let's do a couple of examples here, and then we'll kind of talk about the mechanism. This should be fairly quick, though. I don't think it's going to be too bad. If you understand hydrohalogenation of alkenes, then you're definitely going to understand hydrohalogenation of alkynes. There's just a couple little caveats to the reaction. So let's start off with this 3-carbon alkene, all right? So, and then what I'm going to do is I'm going to put this with excess HCl. So I can use HCl, HI, HBr, whatever, it doesn't matter. So I'm going to put this with excess HCl, and we'll talk about the excess HCl here in just a second. So what does this do? Well, it adds HCl to this triple bond twice because there's 2 pi bonds, right? So the addition of HX can happen 2 times. So that means that this chlorine is going to go on the more substituted carbon twice. So what is that going to look like? Well, this carbon has 0 hydrogens, and this carbon on the right has 1 hydrogen. So the Markovnikov's rule would tell us that the hydrogens are going to go on the right, and the chlorines are going to go on the left side, right? So I'm going to get rid of both of the double bonds. My 2 hydrogens went here, and so that means that my 2 chlorines went here, okay? So I made a geminal dihalide, okay? A geminal dihalide. So that's what this looks like with a terminal alkyne, okay? We'll talk about the mechanism of that shortly. So this excess HCl, same thing as if I said 2 equivalents of HCl, right? So I can say 2 equivalents of HCl. So this just means that I'm going to be adding HCl, or I'm going to be adding 2 moles of HCl for every mole of this alkyne that I have. Again, that just gets me the exact same thing. It gets me 2 chlorines in the Markovnikov fashion. All right. So then let's take a look at it and see what happens whenever we add 1 equivalent with a terminal alkyne. So we add 1 equivalent of HCl. Well, that means that we just get rid of 1 of the double bonds and add a chlorine, or 1 of the pi bonds, excuse me, and we're left with a double bond, right? So I'll draw this here. So we're left with this, right? So with a terminal alkyne, typically we would get both isomers, E and Z, but this is not E or Z, so we can't really get E or Z with this, right? So all I get is just removal of 1 of the bonds, and then I put a chlorine on the Markovnikov carbon, okay, for terminal alkynes. All right. So now let's take a look at this whenever we have a unsymmetrical alkyne. So again, we have 3 carbons on this side, but then on this side, we're going to have 2 carbons. All right, so we have 1 carbon here, 2 carbons here. So now let's add 2 equivalents of HCl. Or actually, we'll use HBr this time. Why not? So we'll do 2 equivalents of HBr. So what is this going to look like? Well, remember Markovnikov's rule over here told us that the hydrogen would get added to this carbon because there's 1 hydrogen. So hydrogen gets added where there's more hydrogens. And this carbon on the left had no hydrogens. So the chlorine added there. Here, both of these carbons in this triple bond have 0 hydrogens, right? They have an equal amount of hydrogens. So it doesn't matter where I add the bromine. So that means that I'm going to get both products. So this is 1, 2, 3, 4, 5 carbons long. So 1, 2, 3, 4, 5. And I'm going to get an alkane because 2 equivalents is going to get rid of both of the pi bonds. And so I can either add both of the bromines on this carbon, or I can add both of the bromines on this carbon. Okay, so I can get 2 different geminal dihalides. So either the second carbon will get both bromines, or the third carbon will get both bromines. And so these are my 2 possibilities that I would get here. So it gets slightly more tricky whenever we see a internal alkyne and not a terminal alkyne like this, okay? So now let's take a look at an internal alkyne with just 1 equivalent. This is the trickiest that this reaction is going to get. So we're going to use the same internal alkyne, but this time we're going to use 1 equivalent of HBr. So what does this look like? Well, again, I either get bromine on this carbon on the left or this carbon on the right, right? So I get bromine on one of those 2 carbons. So again, let's do that. And I just get rid of 1 of the pi bonds this time, right? So I get this one as one of my products. And I also get this one as another one of my products. Okay, so I get these 2, but then the other thing to mention is that this forms both isomers. So you'll notice that this isomer right here is a Z isomer, okay? So both the highest priority groups are on the same side. So this ethyl group and this bromine are on the same side. And this isomer right here is also a Z isomer. So this methyl group and this bromine are on the same side. So I'm going to get the E isomer of both of these as well. So what does that look like? Well, I'm just going to take the bromine and this methyl and flip them. And then I can do the same thing here. So that's going to look like this. So I get 1, 2, 3, 4 products for this one. Okay, this is as tricky as it gets. All right. So again, this one is a Z isomer because the bromine and this ethyl group are on the same side. The 2 highest priority are on the same side. This is also Z because this methyl and this bromine are on the same side. And then this is E because the ethyl and bromine are opposite. And this is E because the methyl and bromine are opposite. Okay. So I get both E and Z isomers. So let's say that. So I get both E and Z where possible. Here, this can't be E or Z because I have 2 hydrogens over here, so I can't differentiate between these 2 hydrogens. So this is not E or Z, so that's why I just get 1 product for this one, okay? So, but here, whenever I can differentiate between E and Z, I get both isomers. And I also get either bromine here or bromine here. So that leaves me with getting 4 totally separate products. Okay, so this is not a very good reaction. We have a lot of stuff that we need to separate. So definitely not great. But this is basically everything. So if I have excess HCl or 2 equivalents of HCl, or 2 excess or 2 equivalents of HX, right? It doesn't have to be HCl, it can be anything. With a terminal alkyne, I get a geminal dihalide, and I just get 1 product. 1 equivalent is going to give me, with a terminal alkyne, is going to give me this vanillic halide. And then two equivalents with a internal is going to give me two different geminal dihalides. And then one equivalent with an internal is going to give me four different isomers of, well, two different products that each have two different isomers of these vanillic halides. Okay. So that's basically all the different caveats to this reaction. So I think that it would be good to take a look at the mechanism and then call this reaction done. So the mechanism for this is the exact same mechanism as addition of HX or hydrohalogenation in alkenes. The only difference is that it just happens twice, right? So let's take a look. So let's do this one, and we're going to do the two equivalents of HCl. So again, we said that this gave us this, right? So let's take a look at the mechanism. So just like what happens in addition of HX to alkenes, one of the double bonds, or one of the pi bonds, is going to come and take that hydrogen, and the chlorine is going to get deprotonated. So then this hydrogen adds in a Markovnikov fashion. So the hydrogen adds where there's more hydrogens, which was here, and then I just have one bond left. So that means I have a carbocation here on this double bond, which is a vinyl cation, all right? And so then this Cl minus is going to come in and it's going to attack that carbocation, which is going to add my first chlorine. So, and you'll notice that if I just use one equivalent of this, then my mechanism is done, right? So this is a very quick two-step mechanism. But in this case, since I'm using two equivalents, then I have to go all the way. So I just take another molecule of HCl. Whoop, didn't draw the bond, sorry. Another molecule of HCl here. And then what this is going to do is take this other hydrogen, and that's going to deprotonate the HCl, which is going to give me a carbocation again. So this is positively charged here, right? And then that chlorine is going to come back in and add itself to that carbon. And that's it. So then I get my final product, which was this, two chlorines on that. So a geminal dihalide. Okay. So this is as difficult as this mechanism gets. Again, if I was just using one equivalent, then it would have stopped right here at this third structure that I've drawn, right? So it just depends on how many equivalents you use. So again, this is very similar to hydrohalogenation or addition of HX in alkenes. So hopefully this was easy to understand, and hopefully this video was helpful. And in the next video, we're going to be discussing different types of hydration. So the second video is going to be acid catalyzed hydration for alkynes, and then in the video after that, we're going to talk about hydroboration oxidation in alkynes, and then we're going to continue on from there. So hopefully you join me for the next one. I appreciate you watching this, and I will see you in the next one.